Good morning. We have now a session mostly devoted to the dynamics of accretion disks. And our first speaker is our former great colleague, Audrey Trova, who spent several years in Prague. And he was also frequently visiting Opava, and she was also attending several times, even in person. And now she will talk about thick accretion disks in an external gravitational and electromagnetic field. So,
hi everyone. Thank you, Eji, for the nice introduction. So yeah, I'm Audrey Trova. I'm a postdoc now at the Center of Applied Space Technology and Microgravity at Zarm in the University of Bremen. So I would like to apologize because I'm not here with you on site this week. It was a little bit tight with the schedule to be there in person, so I'm here remotely. I will be happy to come again in Opava, of course, soon. Okay, so I will discuss then a thick accretion disk in an external gravitational and electromagnetic field. So we, oh yeah, oh, I change it. Okay, there. We are going to talk a little bit of some introduction and motivation for that work. So accretion disk. I'm sure many of you know that it exists different theoretical model to describe the accretion disk system. They are divided in different categories due to their thickness, their optical depth, or their mass accretion rate. Some well-known models are known as the thin disk model, the ADAF, the slim disk, or the thick disk model. My interest is about this last one, so the thick disk one. So why is that one? Because it's one of the simplest model, then it is more easy to treat analytically. And moreover, it can solve some basic observation related to accretion in active galactic nuclei or in microcrasa. Okay, so that thick disk model possesses also some interesting features, as for instance, a funnel along the rotational axis, which is relevant for jets collimation and acceleration. It has a maximum of pressure, which is possibly also relevant for epicyclic oscillatory modes. And it has a cusp, which is a self-crossing of one particular equipotential surfaces. And this can be, for instance, relevant for inner boundary condition. So the thick disk model, also known as Polish doughnut, so well known by and developed by the team of Professor Abramovich. So is based on the and described on the Euler equation, which can be written on an integral form, which takes so this integral here. So we can rewrite by using some different hypotheses and condition as a total potential. So this total effective potential, which describing your accretion disk, is depending on the metric component, on the four velocity vector, on the angular momentum and angular velocity. So our interest is about the closed equipotential surfaces, which can be related to the accretion disk. One of the other interesting things is that when adding some barotopic equation of state, we can come back from the equipotential surfaces to some important characteristic of the disk as the pressure and the density. But this is for neutral fluid. What happens when we have the electromagnetic field in the game? So when we say presence of magnetic field, it means that we are now working with a charged field, which encircling a compact massive object. So now our accretion disk is going to be modeled by a charged field. So by studying particle motion around Kerr black hole, the team of Professor Stuttlich found the possibility of existence of equatorial circular orbit, here described by this picture here on the left. This bound orbit was possible to find when the charged particle is surrounding a black hole and embedded in magnetic field. It could be a uniform one described by the Wald solution, a dipole, or parabolic split monopole. So directly, it was clear that it was interesting to study the case where we have a lot of charged particle, and then and to search if we can have some toroidal structure in that specific case of external magnetic field. One of the main assumptions of this thick accretion disk is that we have a circular motion, meaning so we cannot really talk about accretion because we don't have any radial movement. And the second big assumption is that we have a non-conductive fluid. So what does it mean? It means that we are in a case where we are in the opposite direction to the ideal MHD, so to the force-free approximation. Then sigma, the conductivity equal to 0, meaning we have an infinite resistive fluid. So the electromagnetic field is connected with the motion of your fluid, meaning the charge is following the movement of your fluid. So it is true that the ideal MHD is an excellent approximation in many astrophysically relevant situations involving fluid in motion, as for instance, when studying neutron star, where the electrical and thermal transport properties of the matter is mainly determined by the transport properties of the electrons. But for instance, in catastrophic event, as merger of two neutron stars or merger of neutron star with black hole, the plasma produced at that moment can have a really high temperature and really very low density. Then in that case, it can produce some regime where the non-ideal effect can appear. Then in this case, our model can be relevant. Okay, so our this charged fluid model, so it's this analytical model. So we are doing this because we want to discuss about the existence and morphology of these toroidal structures, where we can find them, how, with which parameter. This analytical model can also help us to divide the different term. Divided the different term and try with the goal to understand how they interact with each other. So what is the role of the spin by itself, the role of the charge of the central mass if we have charge, and the role of the external magnetic field. And finally, one of the goals of this analytical model is to serve as initial conditions for simulation. Some word about this central object and the electromagnetic field. Sorry. The central mass is usually an isolated black hole, so we can speak about with the no-hair theorem. It can be rotating, then the rotation of the central mass is going to interact with the electromagnetic field. So what kind of electromagnetic field? So usually a large-scale one, so from nearby pulsar magnetar or the galactic field. About the charge of the black hole, it is known that even if it's true that the time scale of discharging the black hole is really slow, it can at least, it can have some influence by itself. For instance, the gravitational collapse of magnetized and rotating neutron star may create a Kerr-Newman black hole. And the merger of charged black hole and neutral black hole may create fast radio bursts. So we know that the charge of the black hole can have an influence, then it's kind of interesting to see its influence, to study it, to add it in our background. So the main question was, does the charge and the electromagnetic fields extremely influence the model? So there was a different study which has been done in the past in different conditions. So one related to the ideal MHD, which is this Komisarov solution where you have an additional toroidal magnetic field attached to the fluid. And then the model developed by Professor Stutlik and his team which corresponds to the opposite direction to the ideal MHD, so the high resistivity fluid. So it started in 2011, and since then we studied different charge fluid with different gravitational background, charge shield, Weiser's neutron, Kerr, and different external electromagnetic field, dipole or uniform, for instance. So I'm going to discuss about that specific model and the results that we had all along these years, the different structures we get. So accretion disk has a charge perfectly. Some basic assumption. So the space-time in the electromagnetic field, they are stationary and axially symmetric. We have a reflection symmetry to the equator plane. The electromagnetic field, this is important, is a test field. So it means that B and Q have low value, which meaning that they don't influence the space-time. So we are going to work with standard metric as charge shield and Kerr. Because we are choosing our electromagnetic field, we can calculate the electromagnetic potential, and we're going to work with AT and A phi. And finally, we can have a charge on uncharged black hole. What about the matter? We have a test matter. So same, the internal force of the fluid are not taken into account. So no self-gravity, no self-magnetic interaction. It doesn't influence the space-time. We have a perfect fluid, stationary and axially symmetric, and as I said at the beginning, the circular motion. So only UT and U phi, no radial movement. So the gravitation, the pressure, and the electromagnetic force are going to act together to form equilibrium configurations. So by using the conservation of stress energy tensor, the Maxwell's equation, and the conservation of the rest mass density, we can get the magnetized version of the Euler equation. So in the white part on the left, this part here, you can see my pointer, right? Yeah. Okay, so the part in white, you can recognize the Polish doughnut equation. And when you had an external magnetic field, you need to have these two terms here. When you recognize the magnetic tensor, the velocity, the charge of the fluid, and sigma, the conductivity. So because we are working with stationarity and axially symmetry, we need that the T and phi component of this equation is 0. And this is only possible if we make disappear the fourth term here on the right, in red or pink. So to do that, we decide to put this sigma equal to 0 conductivity. So the charge are going to stick to the matter. So we put sigma equal to 0, and we can express F with the four velocity potential, the four magnetic potential, sorry, AT and A phi, and we get this final equation. So this equation is kind of general, and now we need to choose the background and metric and the electromagnetic field that we want to study. This is going to be a lead by one important point, the anti-gravity condition of that equation, because if we want to write it as an integral, we need to fulfill this anti-gravity condition. So to do that, we decide to set that part of the equation as one as a derivative. So we need to build this S function, and this is going to be the hardest part, because this S function cannot be written analytically in some different background with different electromagnetic fields. Sometimes it's hard to find it a closed form for that S function. This S function, if we succeed to find it, it means we can integrate. These functions are going to depend on the background that we take, so depend on the spin if we have it, on the charge of the black hole and the magnetic field. Finally, we need to set this F of S function, which is that term here, so the charge times the for velocity. And for simplicity, we decide to put it as a power law. So K0 represents how much your matter is charged. So finally, by choosing these two, by setting these two parts here, we can integrate and obtain the effective potential. So now we can build various structure. So from single equatorial tori, which is going to be, we can model the accretion disk. We can also create double tori, levitating tori, or even polar clouds. So I'm going to start to discuss a little bit about the Equatorial Torus. So W depend on many parameters, and we don't have enough equations. So to start, we decide to restrict our discussion to n equal to 1. So we have a lot of parameters, and we try to constrain them. And Chris Troven, which is working with us, found this interesting catastrophe theory, which help us to have some insight about the value of L, and so the specific angular momentum, AK0, so how much the matter is charged, to get the solution. So here you have this on the red curve is how to say, is how your effective potential behave. If you have a bound-fluid structures, you know that you have a maximum in W, and if you have a cusp point, you have a minimum. So according to the place of your parameter, the value of your parameter, you can have different behavior of your effective potential. So if you are here, you will have only a bound-fluid one. If you cross that line, you create a cusp in the middle of the two bound structures. Now, if you cross the K0 equal to 0 line, you inverse your effective potential, then you get two cusp points with one maximum. And then if you cross again, you will get only an open structure, which here doesn't really interesting us because we just want to close the co-potential surfaces. So you will only have an open one with a cusp. And if you cross again, you will get again the two minimum, so two cusp points with one maximum, so only one bound-fluid structures. So we plot this curve for different value of E to see how the charge and the magnetic field are changing that kind of curve. So E is Q over B, and you can see that the curve is really changing with Q and B. So here we have different value. So the area of your, how is your potential is really changing when you make vary the charge of the magnetic field. Sorry, I don't know why it come back always to that point. Okay. So just some example of equatorial structures that we could build. So here we are in that area here where we are only a bound one. So this is different tori in the equatorial plane with different value of E or different value of K0, which is written K here. So here we fix the other parameter, just make vary E, and when we increase the value of the charge or diminish the value of the electromagnetic field, we can see that the maximum of pressure is pushed away from the black hole, and the shape of the disk is changing also a little bit. It's the opposite when you increase the K0 parameter, your center seems to tend to go in the inward direction. So this is when we are in that area. When we cross that line, oh God. We create this, we can have this this double tori solution, which can be linked to each other like this, or linked just with the cusp. So two tori linked with one point, and they can also be detached from each other. So two tori around the central object. Finally, if we're crossing again, this time the K0 equal to 0 line, we can get solution with an inner cusp. So here on your left. So here we have possibility of accretion because we have a cusp point. And we also have this outer accretion solution where in the effective potential, in the equatorial plane of the effective potential, the cusp point, the outer cusp point is filled before the inner one, and then we could have matter which flow in the outward direction. Okay, so this is for Equatorial Torus again. Okay, and just skip that. We decided to have a look to how interaction are working together in the different solutions. So here we plot the different forces which are in the game in the solution where we have only a bound fluid structures. So this is the acceleration part, the electric force, the magnetic force, and here it's the total force. So you can see that the total force at the end point directly on the maximum of pressure, which was of course expected. So what we can say here, we can probably say that the fact that the inner part is thinner, than the outer part is mainly due to probably the acceleration part, which going to be counteract effectively the electric force and the magnetic force, which are going the opposite direction. What happened when we have a double tori? Here we see that again the total force is pointing on the two different maximum, but also here in the middle on the cusp. So it's more difficult to say how is it why we have the formation of this cusp point. We can see that we have a change of sign in B and in Q, and the force of in the change of sign, the electric force and the magnetic force close to the second maximum of pressure here. And I would say maybe what we can say that the creation of what we can say, if you remember the picture where we have the equipotential surfaces of the double tori, but all the matter was mainly in the first torus on the left, and this probably due to the acceleration part and gravitational part, which is way much bigger than the electromagnetic part. Okay, then let's talk about other kind of solution. I need to hurry up a little bit. So the levitating tori, as discussed at the beginning of the talk, so it was possible to find a bound orbit levitating above the equatorial plane, and it was also possible to find fluid structure above the equatorial plane. So here we have some of them. So we can have them linked to each other, like this on the left, or linked through the cusp point, or completely detached, levitating above the equatorial plane. So of course, it's not, if we have that levitating tori, it doesn't mean that we don't have an equatorial one. So it's possible to have both of them in the same time. Okay, let's say a word about this polar solution, which are more, we'd say, exotic, if I can say that. They are taking the place here of the jet. They are above on the polar axis, and they can take different form according to here the value of the spin parameter. If you increase it, there will be more thinner in the vertical direction and more thinner in the radial direction, and they can take many different forms. Okay, so I'm going to conclude now. So We did those last year about this charge fluid model. So we found very different equatorial structures from open structure with cusp to bound structures, mixing cusp and bound, and possibility also to have a double cusp of double tori. We have the presence of the levitating tori above the equatorial plane. We also found the possibility to have those polar clouds, and which was also interesting that at the beginning there was only possible when you have B and Q together, so charge and an electromagnetic field together. But if you put 1 to 0 or the other 1 to 0, it was not possible to have them. But if you include the rotation of the central mass, it is possible now to have them again. Meaning, if you put B equal to 0, but you have Q and A, you can have this solution. And if you put Q equal to 0 and you put B and A together, you can have the solution again. So it means that at some point, the rotation can replace the magnetic field or the charge of the central mass. Finally, we know that the region of bound fluid depends really highly on the charge of the black hole, on the B field, and on the angular momentum. The models also depend highly on this, on the charge density of the fluid, meaning on this F function. So one of the main goals is for the future maybe is how to constrain this function. And maybe one of the ideas is to work on the stability of the solution to understand on which parameter maybe the solution can be stable, and it can also help us maybe to constrain this charge density of the fluid. Thank you very much.
Thank you very much. Time for questions. So I have a question.
Yeah.
The question is actually, because I didn't kind of catch it during your talk, but all these configurations are having constant angular momentum, or?
Oh yeah. Okay. So some of them, so that the equatorial one here, yes, they have constant angular momentum. Yes, they can have constant angular momentum, or they can have omega equal to constant. The off equatorial tori, if I remember well, I think we only have them with L equal to constant, not in rigid rotation. It's not possible. And the polar cloud, it's the opposite. They are not possible with L equal to constant. They are only possible with omega equal to constant.
And then another question, if there is.
Yes, I think Daniela has a question in the chat.
And how? Yes.
Of course, if there is matter on the axis of rotation, angular momentum there must be zero,
yeah,
because like in Newton's theory. So this, as she answered correctly, but the obvious physical reason is this:
sure.
Constant angular momentum, non-zero angular momentum axis of rotation means infinite centrifugal force.
Yes. And we have one question from you.
Yeah, Daniela has a question in the chat, I think.
And Daniela, so maybe if you can switch off, maybe you can ask Daniela, like, although.
Can you see the question? I have it on my screen, but I don't know if you can see it. No.
So I will read it. Interesting talk. I have two questions. With reference to equation 1, is it possible to have multiple tori, for example, more than double tori, while also considering different rotational law as for rotating and contra-rotating, or multiple rotating structures? Are you always considering a constant? Okay, with reference to slide 12 and 22. So maybe you can answer first this.
Okay, so for the first one, at least with L equal to constant, we only get the double toris. We didn't find any possibility to have more. Maybe I can come back to the, okay, on that plot here, maybe here's better, okay. So this plot made for different value of E, so to have the different behavior. When we increase E really high, I think Chris find a region where we could have two tori with 3 cusp, but two tori with 3 cusp. So one inner one in the middle and the outer one, but we didn't find any possibility to have another tori again, so a third one. So maybe if we try other, as you said, other rotational law, we could try that to see, because here we just only try L equal to constant or omega equal to constant. We didn't try the other one.
If I summarize the rest, she is asking actually about this cast at the outer edge, if it is really true, because it looks like in some of the picture.
Yeah, so we don't want to send this. So here the double tori. So double tori and double tori are all part of the same. Yes, this is the same matter structure. I mean, you have the same value of L. Yes. It's the same structures.
Okay, I'm sorry that because there are a lot of questions. So maybe we should move forward in the program, and Daniela, maybe you can ask Audrey by email. Okay, thank you very much. It was very nice.
Thank you very much.